Right. So today is lecture number 4, and we are going to learn about all different types of processes that helps remove pollutants, as well as which help increase infiltration of stormwater through green infrastructure, different types of green infrastructure. So these are the processes, and again, many of them are already covered in C153. So I will not really go details about it, but I will give you overview. But some of them are recorded, so that means if you have not taken C153, or if you want to have a refresher again, I can always send the link. So I'll do that if you need it, but just let me know. I'll do it anyway on Campusware, so that way you have those links. Only those lectures which has extensive information about this topic. All right, so announcement, reminder office hour every week Wednesday. So I wait for you for 30 minutes. If nobody shows up, I usually leave, unless you tell me to come certain other time. Again, this is just office hour where I put my time off just for you. Doesn't mean that you can meet any other time. You just have to email me and let me know as a team that you need to meet some other time. Again, it's apply also for individual students if you have some certain things to discuss. Quiz 2 will be released after 8 p.m. So that's due next tomorrow, Friday, midnight. Okay, so you have 20 minutes to answer 10 questions. It will be on lecture 1 to lecture 3. So anything you cover today is not part of the quiz. Okay. Homework 1, again, it's out, it's due tomorrow, April 9, via Gradescope. Just upload those scan copy. Make sure that you assign which page or for which number. It helps TA or graders to grade it faster. So make sure to remember to assign that page for each questions. Project, part of the credits are due end of each week. This week I'll tell you. The first week I usually give 5% credit because I know this is not easy to find a groups and all that, because I know some other groups. But this one you got to have it. Something like, I'll tell you more about it. But discuss with TA during office hour, if you office hour or discussion session, which is tomorrow, if you need more help about choosing a topic. But this is the minimum I need from you by this week. One, you have a group. That means you can create a Google Doc where you write your project. So name it with a group name instead of saying that C159 project. Make a name for the group. That way I can uniquely identify your group. Because if you do that, everybody else does it. So it's hard for me to know which one is what. So that's write the team members, um, name the group. I'm just going to write it. You can write any group name. If you're any name is fine. Your favorite dog or cat or any location name or game, anything is fine really. Um, Write the name of the team member so that I know how many members are in this group. Write a tentative titles. Now again, you can change it later, but at least I know from the title, I know at least what you are thinking of. Okay. If you already have met me or TAs and discuss about the scope, write about it. Okay, that way I give you feedback, because the less you write, the less feedback you receive. So it's not helpful to just send this much. So write what you have thinking. Again, you are not losing any credit. You just have to brainstorm. There's really nothing to lose here. I just want to make sure that next week you'll be doing this one. So that's why I wanted to make sure that you have the scope, and you'll be searching relevant research articles or reports next week. So you'll learn how to search all that from Renan this week in the discussion session, as well as you'll release some videos so that you can watch them. But point is, you got to have those keywords so that you can search. That's why we need to have title as well as scope cleared. We'll give you a specific keyword, or we discuss with that, and then you can start looking for those references next week, which is due next week. We want you to learn how to search articles. That's the whole idea of next week assignment. Again, either you email me the links or share via campusware, which is fine. That way I can bookmark it. So anytime next time, I'll just go to that emails and check that Google Doc for any assignment. All right, so learning objectives. This is the first half. Everything that you see over here, you already learned in CE153. Okay, so it's nothing new here. I'm just going to reiterate many of the concept, just skim through it so that you to make you remember. But for those who didn't take this one, or you have taken this class long time ago, there this is already recorded. I share that on the class website, so you can go back and watch it. So I'm going to go through very quickly, but again, these are recorded already and uploaded on class website, so you should check it if you are not familiar with this concept. And you can also go back for the C153 class slides also. I can share those videos as well. The main objective is you learn how to, because the post design criteria for any stormwater treatment system is to get rid of excess runoff. Okay, that's the main goal. So how do you get rid of excess runoff? Is by infiltrating them through ground. So infiltrations, or passing of water through soil, is the first criteria. So those are the things you learn first. So these are the physical process. Number one, infiltration of water. Number two, the physical removal of particulates. If you have a sediment, suspended sediments, particulates, those can be removed by sedimentations or gravity, or filtrations. If you have just a sand layer, you can filter a lot of the large particles. So these processes are all physical processes, and we are going to learn that in the first half of this class. And again, we have covered many of them in the fee 153, so I'll go through those quickly. The one which is new, I'll explain a little bit more. But again, these are already recorded. You can watch them. That's why I'm not explaining very quickly, very long here. All right, infiltrations. The infiltration means water moving through soil. Okay, it pass through a porous media. So that's the primary functions that will reduce flooding, or that will reduce the runoff volume reductions. By default, if you are removing storm water away from the surface, you are also removing pollutant along with that. So that's why it's the first criteria. So now question is, what kind of physical parameters or things that you can use to compare between green infrastructures? And so those are, um, one of them is hydraulic conductivity. Hydraulic conductivity of this media. So this is the media, water moves through here. So for that, you got to understand what's the conductivity, or how quickly water can pass through the system. And that measurement is hydraulic conductivity, usually we express as K. Okay? And this is basically you can control. Um, so why it is needed? Again, you know that uh, if you have any location, you don't want to have more than 24 hours of ponding. For instance, here is one of the map you see. Every time it rains, you might see some residual water here. So if ponding stays more than 48 hours, that means it's a breeding ground for mosquitoes. So we do not want to have that. The only way to control is by removing or increasing the hydraulic conductivity. So that's why it's important to design the system in a way that you can not clog, or you can continue to infiltrate water as a faster rate. So the way you can control is by adding a material which has high hydraulic conductivity. So this is just one example of different materials you can use in stormwater infrastructures. So as you can see, most of the time, if you use something like too large, let's say gravel, if you see that hydraulic conductivity is um, pretty high. Okay, so the highest is, as you see, gravel is pretty high. Highest is gravel. That's the highest one. because it's 3 times 10 to the power minus 3 meter per second. So that means you can multiply times 3600 to get the number for 1 hour, because 1 hour is 3600 second. Um, so, but normally you could expect that why not use gravel? Well, people do use gravel to some extent, but gravel is, it allow water to move quickly, but later you realize that that's also not good for removal of pollutants. So you need to have some control. So that's why most of the time people use sand, and the sand type used is mix of this. Okay, so this is, sand is the preferable media. As you can see, medium fine coat, so there is mix of sand people use, and a lot of times they call sandy loam. The soil is loam. The reason is, you see, the loam means the the hydraulic conductivity is pretty close to fine sand. So sandy loam soil, usually 70% or 80% sand, and soil is less than 20%. That's the filter media. And one thing you learn here is that clay hydraulic conductivity is very low. In fact, one of the lowest. So that means that will never be used in any green infrastructure. So any times you see there are clay, you will not use that soil at all. Okay, if you have high fraction of clay. So this is not desired. So typically things people use is sandy loam soil. So sand is roughly 70 to 90%. Soil is 10 to 30%. Okay, based on how much it is. But typically the hydraulic conductivity, the most of the requirement is nearly 10 inch per hour. Okay. So this is the desired hydraulic conductivity. So if you have to, it can conduct 10 inch per hour, that's pretty good. Okay. As the reason you don't need that high hydraulic conductivity, but you realize that over time it gets clogged. So you have to account for that by using initial high hydraulic conductivity. So how do you control it? Because you mix this sand and everything, it has its own size. So usually the smallest or the finer particles in the mixture controls the hydraulic conductivity, because that kind of stop the flow or clog the system quicker. So that's why hydraulic conductivity can be equated to D10 size. D10 means what's the 10% of the size, that is the smallest size. In the side distributions, what's the 10% fraction, um, the size of the 10% fraction, which is the smallest size fraction, because if you do the distributions in that way. So D10 is the diameter of the particles, where less than 10% of particle less than that size exist in the system. Okay, so if you know D10, you can predict the hydraulic conductivity to some extent. So that's the way we can control. That means you have to use very small particle, very large particulates if you want to control K. And hydraulic conductivity also depends on porosity. Usually the higher porosity means higher hydraulic conductivity. Obviously, we are not accounting for clay here, because clay has high porosity, but it has low conductivity. You know that clay is not used, so that's why we're not accounting that. So normally, this is the equation you can use to predict the porosity, how porosity can affect hydraulic conductivity. And why it is important? It's important because many of the system, when you add all these materials, filter media, you can compact them. So even you have large particle size, D10 is same. If you compact them very strongly, their hydraulic conductivity will be very low. So that's why there are two factors you have to control. One is particle size. As the size increases, porosity, the hydraulic conductivity will increases. As the porosity increases, hydraulic conductivity will increase. And porosity will decrease, or porosity increases if the compaction decreases. Okay. So that means if you compact the layer, you will not have high infiltrations. So how do you measure K? The way to measure K is by using Darcy's law. Darcy's law is again used before in C153. Just basically what it means that in a porous media, amount of flow that you can receive, this is flow rate, is equal to hydraulic conductivity times area of the cross section where you are collecting water times the head difference or head gradients. So that's dH by dg or dl, whatever the length scale of the filter media. Um, so if you have a filter media, let's say this is filter media, and this is, let's say, plant, and water is moving here. So this is your L, okay, and the head would be, what is the head difference between this point and this point. Um, so this is whatever the head here, whatever the head here, okay. Um, and usually the water flow from high head to low head, so that's why there is a negative sign. Sometimes, it depends on how the notation was written. Um, so this is the Darcy's law that you know. So if you rearrange this one, you can use the Darcy's law to calculate hydraulic conductivity, because you can measure a flow rate, you can measure heads, you can measure length or the filter layer length or diameter. If you know the filter media diameters, you know the surface area or area. So all these things can be measured. So that's how we do measure in the lab. And also I want to say that hydraulic conductivity is not just function of the filter media. It can be also a function of water. Okay, so this is a one thing written here. If you're so hydraulic conductivity is intrinsic permeability, which is the intrinsic property of materials, times a property of water itself or the fluid media. G is acceleration due to gravity. Acceleration due to gravity, so that's 9.8 meter per second square. And this is viscosity of water or fluid, storm water. And this is density. Storm water. So conceptually, if your viscosity increases, the um, hydraulic conductivity will decrease because it will have more frictions. Um, so this is again, you can use that as a conceptually how to estimate hydraulic conductivity. Again, viscosity also depends on temperatures. If the temperature increases, viscosity decreases. That means if your temperature increases, viscosity will decrease. That means K will increase. So that means, in some cases, if it is a little bit warmer temperature, that means hydraulic conductivity might be a little higher. But that's so small that you can check that experimentally, at least in the realistic case. All right, so this is how we measure. If you have a column, let's say this is the filter layer. One is a constant head test. In geotech lab, you do that normally. So the flow rate again is volume over time, and volume equal to the height of water divided by in times the area. So that's how it is written here, all that. So basically, this is the equations. Okay, um, K is volume is the volume of water that you collect at the bottom as a constant head. H L is the length of the filter media. This is the length, and H is the height. This is height. Okay, and area is this. That will be pi d square divided by 4. This if it is a circle, and time is just how long you collect that water. So because if you are collecting water here, okay, this is the volume, and you are also collecting at different time, okay, because you can collect at certain time, so that's the time. So if you know all these values, then you can predict that equations. Then there is also a falling head test. Sometimes it's um, this is a this is the constant head is used for core scan trial. Means if the hydraulic K is very high, the K is very low for the soil, let's say clay soil, that's not going to work because it takes long time for to get some amount of volume of water. Because this system over here, you depends on the volume of water collected. If the volume takes long time, that may evaporate. So that's why it's important for those cases use falling head test, where instead of having the head constant, you are letting the water drop. Okay, and so what you are checking here is the how long it takes before the the water fall from one height to another. Okay, so let's say this is h1, this is h2. The waterfall, whatever time it takes, then you can plug this value over here, and everything else is same. So this is L, this is H initial, this is H final. So if you write this equation, you basically are going to solve this equation. So if you solve this equation, what it means is area cancel. So that means you get dH over H is equal to K over L dt. So if you um, integrate them, initially when time equal to 0, the height was H initial, and when time equal to T, after a certain time you are measuring, height is final. So if you solve this one, hold on, what happened? No, that's not the one. Um, if you solve this one, this will be, I'm solving here, okay? So this is LNH, its initial, its final, equal to, it's going to be K over L times T. So that means this will be ln h final by h initial. So it will be ln h final by h initial equal to k by lt. So that means if you rearrange this equation, so it will be k is equal to L over T. So this is a mistake here. So this should be final divided by initial. Okay. So that's how you solve it. But bottom line, you should just know that the equation, that way you can solve a questions. So this is something you can do in the, if you have a materials and you are deciding which materials to use for filter media, this is how we test it in the lab. But if you have to do it in the field side, you can't really, make this soil and collect somewhere. So what you do is it's exactly same method. You put this double ring and you fill basically in the center, you fill the water up to here, okay, certain height. And then inside ring, you can fill certain height too. And you can control that by using this tube. And then basically you're looking for how long it takes for that water to drop. Okay, how long it takes for the water to infiltrate, and you are measuring the height, and based on that you'll be able to calculate the hydraulic conductivity. So it's called ring infiltrometers, and this is something you people buy. And there is another method is borehole method. Basically, you create a borehole and you insert and measure velocity of constant area. You keep fill water and then you see how much water you have to inject to maintain that flow rate. But bottom line, there are methods. We are not going details about it, but the principle is very much same. So there is examples. Again, I'll how to solve these questions. Everything else is given. Diameter is given. Height, all those numbers are given at different time. So it asks you to calculate K. Okay. So these are different values. So now how do you calculate K? Basically, if nothing else is, now let's see what else is given. Um, Ask determine the K of the filter media using the biofilters. If the media depth was 42 centimeters and diameter of the biofilter was 5 centimeters. So the diameter is given 5 centimeter, then you know the area, pi d square by 4 if it ever needed. And then your length of the filter media is 42 centimeter. So which is here, okay. Um, and then so basically it's given you this value. So how do you solve this one? um, well, you have different h value. So one way to solve is for each one, you can calculate a k, then you can do average, or you can just make equations and draw the straight lines and see the slope. For instance, if I write this one, ln h1 by h2, so if you calculate this value for each pair, it will be um, k times t divided by l, right? So that means if you plot this value versus t, let's say this is y and this is x, this will be m, okay? So this will be slope. So slope would be k by l. You already know l, then you can calculate k value. So the graphically you can also calculate that value. Another question, how long it would take 20-meter ponded water above bioswale? All right, so I'm not going to read this one because already I solved it, recorded it. So you should check this one, try to solve by yourself. If you can't, then you can always watch that video. All right, so the next one is sedimentations. So the concept of sedimentation is simple. Like you have a ponds like here. The whole idea is the water moves here and the water stays for long enough time for the particles to settle. So usually the larger and heavier the particles, it gets settled faster. So larger means D is high, and heavier means density of particle is high. Okay, density. This is size. So that means velocity of settling is high. Settling velocity is higher. So those are the concept, and there are equations to predict it. It's a Stokes law. We learned that in CE159. It basically balance drag force with viscous force or drag force with a buoyancy and a gravity, the gravitational pull. So this is the equations. Again, I'm not solving this one. You just know that how it is solved before. So alternatively, what you have to remember is the particles will settle faster, means it can be removed faster. If the size is large, which is the d, so that means if the d is increasing, it's increased by velocity is directly proportional to particle size square. So that means it's very sensitive to size of particles. It also depends on the density. Density difference between water and particles. Water is one or constant. You can assume that. So that means it depends on the density of particles. And then also depends, velocity depends on um, density of particles by density of water. So how different it is from the medium. Sometimes density of water can change. For instance, if you have salty water, the density of water itself is higher. So that means particle can stay float for longer time. Um, then velocity is inversely proportional to the viscosity. Again, you know this one. If you have high viscous samples, water will have more friction, so it will not settle. Um, so what's the design? Again, from Stokes' law, you know that you just have to maintain the water long enough. So that means it depends on the overflow rate, which is a flow rate divided by surface area, which is the entire area of the, this is area. Okay, if it is overflowing, because water is not moving from the bottom, it's only the, it has to it has to flow across the bank. Okay, so this, if you have the pond here, water will only move from this direction. So that's why the area is here. Okay. So your overflow rate should be equal to settling velocity for it to be all particles to be removed. If your settling velocity is smaller than overflow rate, obviously, um, or another way to say is if the if it takes longer time for particle to settle, then obviously some other particles will not be removed. So again, this is in C153. You have solved it. I have also solved it in recording, so you should watch that later. I'm not going to go through this one. Again, this is just another way to say is how you design the pond. If you know what size particle you want to remove, here what I did is I equate the settling velocity is equal to the overflow rate. Overflow rate. Um, this is the condition for all particles to be removed. So when you create that one, you basically know what size particles are going to be removed for a certain size of pond. So that's how you can calculate the size. Again, this is all in C153. We use these equations and we solve it. I also again recorded it, so I don't want to just repeat again here. If you didn't know this one, watch that video. It's only 6 or 7 minutes. You should be able to solve. The next one or the last one about physical process before the break we have to cover is filtration. This is something you may not cover in green first in 153, but I just want to see. I forgot whether we cover that, so let me explain a little bit more. So what you learn over here is that all these um, pond can remove particulates which are small enough or which is large enough to settle or which are heavy enough to settle. But one of the limitation for this design is that pond is usually you need larger space for allowing that time to settle. And that space is not available in many of the locations like Los Angeles. So that means if your goal is to remove sediments, you don't have space for it to create this system. So that's the reason the alternative process to remove is filtrations, which is very efficient. All you have to do is allow water to move through a porous media. And because the pore size is small enough, they'll remove all the particulates. So as close as keeping a sand filter. It's just filling the entire hole with sand and letting the storm water going through that. So that is we call filtrations. So this is a filtration means when water is moving through a porous media and things are strained out of the system. For physical filtration or straining, and then there is a chemical filtrations. So let me explain the differences. So if you have a particulate here, okay, imagine this is particles. So these are the grain, the filter media, okay. So you have a particle that you want to remove. Let's say that particle is this one. So that means when it goes through here, it will be filtered out. Because the pore size here is much smaller than the pore size here. But if the particle is like a little bit smaller, like this will not be, this will pass through. Okay. So that's called straining. It all depends on the relative size difference between the particles that you want to remove by the filter medium particles. Whereas the physicochemical filtration is a little different, where the particle size are so small, but yet it can be removed. Let me explain how. So let's say this is the grain size. And when the small particles come very close in proximity of another particles, it can also be attracted, okay? Because there may be some attraction if the charge is different, or if a particle is just by gravity, it can settle here or settling. Another is if a particle is moving, it can be intercepted, okay? Because just as moving, it hit another particles, and during that process, it may stick with each other. So these are all these processes we call physicochemical filtration. The reason is even the small size particles are there, they can stick because of chemical forces. So we'll explain that one. Give me a second. Let me see what's. I'll be back for a second. You can watch these slides. I'll be back in a minute. All right, so the straining, which is the equation over here, again, this is a equation that shows how amount of particles that can be removed by straining. All I want you guys to remember or think of is this. So straining means how much particles that can remove over time depends on a constant, which is called straining coefficient. And that depends on the relative size difference between particles that are supposed to be removed and the filter media particles. So that's here. dp is the size of the particles, okay, the particle that you want to remove, and d50 is the medium grain size of the filter media. So that's why I say. So what you learn from here, it means if the removal by straining would increase if k is going to increase, and k increases if dp increases. Okay, dp means the size of the particle that you want to remove, which makes sense if you think of how straining it means. It says that if you have larger particle, it can be easy to filter out. That's all it is saying, which makes sense because that's how the size. Another thing is, it says that you can filter a lot more particles if you have the filter media particles are smaller, which also makes sense because if your filter media particles are smaller, they are closely packed. So that means the gap between them is so small that can remove a lot of particles just by physical filtrations. So that's the concept that I want you guys to remember. Nothing else. All this equation, everything is already there in that papers. The link that is given to you. So if you use as a concept for for a grad students, this is a paper to read. Okay. So again, what you learn is that straining, removal by straining would increase if particle size is bigger, or the medium or the media particle size, or the filter media particle size, which is D50 or 50% is smaller. Okay. Those are important for the quiz. So straining are very helpful to remove sediments, but it can be also over time, if you remove a lot of sediments, they can also clog the filter media. So that's why it's a problem in long term. That means your infiltration is going to decrease. If infiltration decreases, then obviously you can't treat any stormwater. So there are ways to ensure that the infiltration remain high for long period of time, so that you don't have to maintain it. So a couple of things you could do is you create a first thing, number one thing to do is make sure that you use very high hydraulic conductivity to begin with. So that means even it clog or the infiltration slow down, still it improve, it still remove a lot more than what you need, which is over here, so that you have more sandy. Again, all you are doing is you are increasing D50. Okay, that's what you're doing here, so that clogging is less. The second is to increase the depth of filter media. Why you have to do it? The reason is most of the particles are filtered at the surface, not in throughout the media. So if you have a deeper soil layer, you can remove that top surface by just scraping it, like how it says here. So if you remove that one, then you still have the rest of the media functional. So that means you can just time to time, you just go there, remove the top 1 centimeter of the sediments that deposited over time. And then you have a good filter media to work with. The natural you can do is adding also vegetations. The reason is, as I said, if you have vegetation, they grow, the root grow through the soil, and that helps the aerations and also create the gap, because the root will die and that will leave behind those gaps. So this is a paper again for grad students. If you want to know more about it, what they did is they create two control media where they measure the conductivity with and without vegetations, and you see in all nearly all the cases, the with uh, with the vegetations, the hydraulic conductivity increased over time. Whereas in other cases, when there is no vegetation, the hydraulic conductivity decreases compared to the initial K. And that's again because of the roots. Um, so the last one is physicochemical filtrations. As you know that filtrations depends. This is where the particle is so small, still it can be removed. And this is applied to bacteria or viruses because they are very small particles and the usually pore size are much bigger than the a virus or bacterial size. So what it means that if it goes close to the filter media, they can be removed by any of the three processes. One is by diffusion, like it says here, because the reason is if you have any filter particles, let's say think of the distance here. When I talk about distance here, within a micrometers or within maximum 10 micron distance. So the soil, the water around it, let me make a different color. So you have water here, okay? So any particulate here near that surface will experience one of the three processes. First, if there is no advection or no water flow, then things can diffuse, particles can diffuse any either directions because of Brownian motions. And when they diffuse, they can actually hit the particles or collector surface. That's what it's called collector. Collector means the filter media. Okay, it collects all the particles. So because of diffusion, it can collide with that collectors. It can also collide with the collectors if the particles are so heavy that it's settling above it, which is the gravitational settling, which is Stokes' law. And there is a third process, which is called interception. Interception means, if the streamline is moving such a way that the particles are so big that it will hit each other. So these are the three reasons why particles can collide. And again, collision is the first reason why a particle can stick. So for a particle can stick, it has to collide fast. So how it is going to collide, what's the efficiency of collision to occur, it depends on all these three processes. So you can see these are the equations and each term describe collision because of one of the reason, either diffusions. So ND is diffusion, this is interception, and this is settling. And they are all depends on certain things. So let's think of conceptually what does that means. So settling is a big factor if the particle velocity or velocity of settling is much higher than the water velocity. So that's why you can see that velocity of settling is, by Stokes law. If velocity of settling is greater than, much greater than velocity of water infiltrate, that means it has more time to settle. So why it is essential for design. So what it means that if you have a very hydraulic conductivity and water is moving so fast, the particle doesn't have enough time to settle. So that's the reason if your K is very high, you are not removing a lot of particulates. So that's why you can't keep the K very high. That's why you're using those sand. And the second one, interception. If you think what is the interception mean, is similar to straining. The only difference here is that it is the particles are just colliding because the streamline is passing through that near the surface. And again, it only occurs if you collide if the particles are big enough to collide. Okay, so all it means is that the particle size is higher, you are more likely to have collision near the edge. So all it means is that. Okay, same thing if the media filter media size is smaller, it will also more likely to collide because the gap will be small. It's similar to straining concept. So you just remember the conceptually what does that mean. Okay, um, the particle size is smaller, then more likely to intercept. The last one is diffusion. This is something diffusion depends on temperatures as well as particle size. If the temperature is high, they will diffuse faster because the thermal vibrations. If the particle size is big, diffusion is not going to occur because heavier particles will not move faster, okay, because it's a random motions. So these are the conceptual you can think of. Any quiz question, if I ask, if you increase the temperature, is the diffusive collision is going to increase or decrease? Just by looking at the equation, you can predict. So just remember this conceptually. Again, you have all these slides accessed to you. So that's how you can do it. And so now that you learn all that collision efficiency, why it is important? Well, this is important for you to predict how much particulates that can be removed in a system. So the removal efficiency is basically whatever the initial amount of particles that coming out coming in minus what's leaving the system. The difference is what is removed divided by what's the original particles. Okay, so that if you arrange this equation, so you know this one will be 1 minus n by n0. Okay, and n by n0 is something you can measure because you know what's the concentration coming in, what is the concentration leaving the system. But that can also tell something about your filter media. So that one, n by n0, is a function of the length of the depth of the filter media. So this is the length of filter media, and this is a constant. That constant is a function of this collision efficiency and attachment efficiency, all that. Okay, so why it is important? Because if you know this is the particle size of filter media, this is the collision efficiency, this is porosity, this is a alpha is a how it's attachment efficiency, which is determined by experiment. You can't determine by theoretical. So if you know all these number, you can actually design your system such a way that you can predict it. Because a lot of times you can vary any of them. For instance, you can vary the collision efficiency higher, or you can decrease the porosity, or so that the attachment efficiency will be higher. So all these things you can see how you can use those to predict the removal. So again, we are not going to use any of them, and this is just to show you that these attachment efficiency, all that depends on different empirical equations are developed. People use those equations. So again, you don't need to remember any of them, but just know that these are easy to way to calculate. So I just already explained those things. This is just example. Again, these are all recorded, so you don't need to understand or remember it. You can watch later if you need to. So that's all when it comes to the physical process. So I'm going to have a learning assessment questions. You should know that what are the two design factors that will increase infiltrations. You know that you have to increase the K, and for that you have to increase the particle size or the porosity, all that other factors that you have to check. So go through these questions so that you know whether you understood those what is in the slide. If you can answer these questions, you have to watch those videos. Okay. For now, let's have this quiz. Quiz. This is again a practice quiz for you. Um, just learning assessment related to what you learn now. So let me share the generic questions where you know the question over here and you're going to answer those quiz based on what you learn now. Okay, so hydraulic conductivity of filter media doesn't depend on the following factors: particle size, porosity, viscosity, depth of filter media. Again, whatever you remember, it's really, this is just we cover. Okay, 5 more seconds, I will close it. Choose anyone. Again, this is whatever comes to your mind. This is by no mean, this is just for your own assessment. All right, I'm going to end the poll now and share the results. Again, this is anonymous. I'm not, no, I don't know who answered what. I also don't want to know. But you can see what's the answer here. The correct answer is D. I'll tell you what which slide it is. If you go back, Hydraulic conductivity is related to increasing permeability. That's over here. Okay. Um, so you know that it depends on viscosity. Okay, that's for sure. It is not independent of this one. But also we know that it depends on the particle size. That's where the D10 or D50 come in. There is a D10 somewhere. Where is it? Here. It depends on the size of the particles, and also it depends on the porosity. So again, go back to those things so that you assimilate about those informations, and then you can answers. Okay, so the all those things are given there. All right, so what's the next questions? Stop sharing. So relaunch. Settling velocity. Which of the following factor would increase settling velocity? Increase in particle size or increase in um, viscosity of the fluid, increase in depth of the water. I'm asking what will increase the settling velocity. You have 20 more seconds to answer. 10 more seconds. Again, whatever comes to mind, because you're going to learn from it. So it's not really. And feel free to share if because very important to know what's the wrong, which way you can get to the wrong answer, because that's a lot of people who will have a similar problem. All right, and Paul, share result. The correct answer is increase in particle size. Again, as I said, how fast it is going to settle depends on two factors for sure. You know that the viscosity, that velocity is a particle size square, density of particle minus water divided by a viscosity term. Okay, there is other constant here and there. Okay, so G is here, some constant here. Um, so that means it increases with particle size. It decreases. If the viscosity increases, the velocity will decrease. Okay, so that's why you can't use this number B. Increase in depth has nothing with velocity because it's just moving. Okay, because water density doesn't change with depth, so that means you can't use it. Okay, so that's the second answer. What about third one? Which of the following factor would not affect clogging rate? So I'm asking one of those factors will not affect the clogging rate. Increase in particle size, increase in plant density, increase in area of the filters, increase in depth. So check that's related to here. Okay, so the clogging, as you can see, it has given all these factors. Okay, so if you see that value over here, so one of them is correct answers. Okay, so you have 10 more seconds to answer. Um, but again, this is a learning opportunity for you to go back and to think about it. These are the questions which will be relevant for your next quiz, not this quiz. Okay, I'm going to stop the quiz, the timer in 4 seconds. All right, so share the results. As you see, you know that I'll get to the point. Let's see elimination, increase in particle size. If you increase the particle size, the pores gap between them also going to increase. That means your clogging would also decrease. So it's you know that straining is going to decrease. Increase in plant density. You know that plant roots are helping increase hydraulic conductivity from that. So that means this cannot be answered. Increase in area of the filters. So think of this way: the area of the filters means how wide they are. Well, if you see what happens if the particles move in a one pore, it doesn't have, it is not influenced by how big the filter is because it's all about that locations. So even you increase the area 10 versus 20, the particles still need very small pores to move. So it's really not going to change much. Um, I mean, technically, you know, that's if you are looking at the physical process. So this might be answered. So let's look at the next one. Increase in depth. Both increase in depth and area of the filters are kind of similar concept. But as you know that most of the particles are removed in the top surface. So if you increase in the depth, you are not clogging the rest of the filter media. Okay. So that means what you are saying is a different way to say is this is the most likely the answer. Okay. So that's why I saw this slide. But as far as thinking is concerned, both have the similar concept. Filter and depth normally do not affect that much because you are just depend on that one locations. But if you have higher depth, you have more chance to keep the filter for longer period of time before it completely exhausted because it slowly exhausts with time. The last one. Stop sharing. How would flow rate affects filtration rate? If you increase filtration rate, is this going to make it easier to filter particles or it is going to make it difficult to filter particles? Related to collisions. Okay. So think of if you are passing through very quickly. Um,
Professor,
yes.
is this question asking about an increase or decrease in flow rate affecting the
Oh,
filtration
you're
rate?
right. This is a wrong. So let me relaunch it. Okay. You're right. So this is a how would increase in flow rate affect the filtration rate? So think of if you increase the flow rate, the particle has more chance to filter out or less chance. Think a lot of times conceptually without looking for equations and all that. Okay, I'm going to stop it in 5 seconds. Okay, so share the results. So increase in flow rate would decrease the filtration rate. I'll tell you why. Well, there are a couple of reasons to think of. The number one, it will increase the interception rate, not interception rate. It is going to um, normally it doesn't have enough time. Okay, because even the collision occurs, it also can also knock out those particles. So normally we see that if you increase the flow rate, it does have less filtrations because particle move so fast that it doesn't have time to it just they go through the pores faster. And even there are some deposited particles, they knock out the system. So But I can understand how you can also think it can increase the filtration, because it also collide, it increase collision, because they're moving faster, they're more likely to collide. But problem is that even that collision occur, the attachment is not going to occur. The attachment efficiency, all that will decrease in the next one. So just know that, if you increase, that means if your high rainfall happens, very high intensity rainfall, your capacity of filtration media is going to decrease, because it doesn't have enough time to attach to the system. So that's all for the first step. Let's take a break for 10 minutes. When we come back, we'll discuss about biochemical process. Again, these are things you already know from CE153, so I'll go through quickly, but it's just a refresher so that you know how to use those for stormwater concept. I'm going to stop recording now. For biochemical process, so we learned that for particulates or small bacteria or any particulate substance, we can remove by physical processes, which is filtrations, settling, as well as physicochemical filtration, which is attachment. And now there are lots of dissolved pollutants which are difficult to remove in green infrastructures. So those are for those you need biochemical processes or biological and chemical processes. So the learning objective is that you got to at least identify what are the different processes are, what are the chemical, what are the biological process in stormwater treatment systems. And then if you know this one, how what affects them, you can actually design it such a way that you can increase these processes. So for instance, you add certain amount of amendments that can enhance these processes. And you can use some of the chemical process is redox process, where you can transform organic pollutants. So you can learn to use redox equations to estimate amount of reactants or oxygen is needed for degradation of certain pollutants. And then you learn the degradation process. So again, the type of chemical process are adsorption, precipitations, transformation by redox or other processes. Again, these are you learn in C153 as well as some other aquatic chemistry if you have taken this class in. So there will be some overlap. Okay. Uh, so these are the chemical process. When you have a contaminants which can be removed or dissolved pollutant, they can be removed by adsorptions. Adsorption means sticking on a materials. So that's adsorption. Then there is a precipitations, which doesn't require any filter media. It's just the dissolved pollutant itself. The concentration rise so much that they can bind with each other and produce a solid or salt. Usually that's the case for metals. A lot of metals have very low solubility. For instance, lead or mercury. They can adsorb as well, but they can also precipitate if you have phosphate or certain ions. Then you have redox process. Redox process is, you learn that in C153 is basically transform of electrons to alter that molecular structure such a way that it become less toxic. Inactivation is for pathogens. This is for bacteria or viruses where you make them less effective. They are not have life. So that's more related to disinfections. So adsorption, again, you learn that in C153. This is basically you have a materials and there are dissolved pollutant from water to move from this pollutant to the solid media. Okay, so that's adsorption. And so if you mix a certain amount of storm water in a filter media for a while, you will see that the concentration of the pollutants in that storm water decreases. After a point, it doesn't change much. So that's what we call CW. CW means concentration of pollutant after it has some of the pollutants are adsorbed or in equilibrium. And that concentrations in stormwater depends on how much contaminants already present in the filter media, which is CS. CS is concentration in the solid or filter media. And they can be related by a coefficient, which is a KD here, and we call that linear adsorption. What it means is if you increase the concentration in stormwater, more and more pollutant equivalently will go into the filter media. And that KD is what's the controlling or design factor here. KD depends on fraction of organic carbons times KOC, or adverse or attachment coefficient, or adverse affinity of that contaminants towards organic carbon. So fraction of organic carbon. Okay, thank you, Shane. Can you close it? Yes, thanks. Give me a second, Shane. I'm teaching now. Go, go, down. He finished sitting, so he came back to show that he finished. All right, so KD, which is a design factor, which is basically how was the affinity of contaminants towards that filter media, depends on two factors. One is the fraction of organic carbon in that filter media, and this is basically assumption is that you are talking about organic pollutants, not any other. So fraction of organic carbon is a design factor. So how much organic carbon in your filter media? And so this is the reason why you are adding compost or biochars or activated carbon. Okay. What you are doing is an essential, you are increasing the amount of carbon in your filter media by adding them. So that means there are more carbon, more organic pollutants has more site for adsorption to occur. And KOC,
Professor,
yes.
what was CS and CW again?
CW is the concentration in water. CS is concentration in solid.
Got it.
Filter
Thank you.
media. Concentration in solid filter media. And this for water, okay, or storm water. And KOC is the affinity of pollutants to organic carbon. Okay, so that's why it says OC. Okay, and KOC can be determined experimentally, or it can be correlated with another fraction called KOW, which is something you probably learn in other classes, including CE159. So now question is conceptually how you improve this adsorption or affinity. So there are multiple ways you can increase adsorption. Adsorption is a surface process. So that means you have to have more surface area for adsorption to occur. So that means adsorption can increase if your surface area increases. Another is if your surface charge changes, that also help or not help adsorption. For instance, if your pollutant is an ionic, for instance, ions, metals, let's say positively charged. So having a negatively charged filter media helps because it can bind them each other. So that's the reason ammonium, which is one of the nutrients, is very easy to remove in stormwater treatment system because most of the compost or filter media are negatively charged. That's why they can stick with ammonium. For the same reason, you cannot remove nitrate by adsorption because nitrate is negatively charged and most of the filter media is negative. So if you have a filter media with negatively charged, so this will be repulsion. But at the same time, if you have ammonium, which is another nutrient, nitrate, it's attractions. Okay. So that means surface charge can also influence removal of pollutants. Just know that most of the compost, most of the media that you use are usually positively charged or negatively charged. So that means if you want to remove something negatively charged pollutants, you have to create that positive charge media. In fact, that's the reason iron oxide or iron media is used because it can have positive charge at some pH so that it can stick with some of the negatively charged pollutants like bacteria. Bacteria surface in general have net negative charge because it has phosphorus or phospholipid. Phosphorus is negative charge. It also depends on organic carbon content. You see that FOC or fraction of organic carbon. So if you have more organic, it will remove more organic pollutants. The last one is something also very important. It depends on the mass transfer rate, means how fast it can move. And that is controlled by the advection. So if the stormwater is moving very fast, you don't have much time, as I said. But if the stormwater has more time in the system, so that means you slow down the stormwater flow by any way, it can increase the removal by adsorption. One of the way to do it is keep it saturated somewhere so that it stays longer in the system. So design factor is this, to increase the removal, you have to increase high KD. And that's the reason you add this activated carbon, biochar, etc. Because you are increasing um, the FOC. Okay, if you increase AOC, KD increases, that means absorption increases. So another things to think about is decrease the size. If you decrease the size, D10 or D50, so let's say filter media. This is not. If you decrease the size of the filter media, your surface area is going to increase. Or area is okay. It's going to write it clearly. That means more site. That means KD would increase. Alter surface charge. Again, that depends on what type of substance you are looking for. For instance, you are negatively charged, that means you have to increase the positive charge. If it is positively charged contaminants like metals, you have to increase more negative charge. So this is just one example how much biochars need to be added to biofilters to remove 90% of nitrobenzene from 10,000 liters of stormwater containing 10 milligram per liters of nitrobenzenes if kd of biochar is 100 liter per kg. So let's see what is given here. Your removal should be 90%. Okay, so that means one other way to, this is basically C out by C in. Okay, 90%. Okay, or equal to 0.9. That means your C out would be 0.1 C in. Okay. Then you have the volume. You have total amount of volume is 10,000 liter of stormwater you want to treat, containing 10 milligram of nitrobenzene. So that means your C in, whatever coming in, is 10 milligram per liter. And your C out has to be 0.1 C in, which would be, if you multiply 0.1 times 10, it will be 1 milligram per liter. So that's the concentrations in water um, after adsorption. Again, this is after adsorption, CW. Okay, and your KD is given 100 liter per kg. So what is the concentration? So what's the assumes of some equilibrium, lack of biodegradations. So what it means that it says, so these are all given to you. Okay. Now question is, it asks how much biochar. Well, you have to know how much biochar is going to be used. You have to know how much biochar capacity. First is how much pollutant to be removed. So think of this way: you have 10,000 liters, and every liter has 10 milligram per liter has 10 milligram. But you have to remove how much you have to remove 90% of that. That means every 10 milligram you have to remove 0.9 milligram, 9.9 milligram out of it for that things to occur. So the amount of pollutant removed or mass of nitrobenzene or pollutants would be C in minus C out times the total volume. Okay, the total different concentration times volume. So this will be, if you write this one, this is 10 minus 0.1 times volume 10,000 liter. This is milligram per liter. Okay, so liter cancel out. So this will be 9.9 times 10 to the power 5 milligram. Okay, that's the amount of pollutants, nitrobenzene. Okay, and now you have to know what's the capacity of um, what's the concentration of biochar or concentration of pollutant in biochar. So that is, if you know that concentration, you know how much concentration of pollutant in biochar is basically, um, concentration pollutant in biochar is a amount of pollutant in biochar divided by mass of biochar. Okay, so that one you all can calculate if you know, um, CS is related to CW. Okay, so if you know this one, you will calculate how much mass of biochar is needed. So mass of, so that means mass of biochar is equal to mass of pollutant, total amount of pollutant you have to remove, divided by concentration of pollutant in the biochar. Okay, so mass of pollutant in the biochar is basically, I'll write this one, divided by CS. If you see from this previous equation, CS, concentration of contaminants in solid, it depends on the concentration of pollutant in stormwater after absorption. So KD times CW, KD times CW, and CW is given, so that means you, um, sorry, this is a 1 milligram. Let me see if I'm writing correctly. This is 0.1 times C in, so that will be 1 milligram. So this is 1. So that will be 9. I made a mistake here. So that's 9 times 10 to the power 5. Okay, so mass of pollutant is 9 times 10 to the 5 milligram divided by KD is 100 liters by kg times CW is 1 milligram of pollutant per liter of water. So um, kg of biochar, so milligram of pollutants, kg of biochar. This is milligram of pollutant. So that way you know what cancel out. So milligram pollutant cancel out with milligram, liter cancel out. So whatever the number is here, it will be the amount of biochar. So that will be 9 times 10 to the power 100 cancel. So 9 kilogram of biochar. Okay. Again, this is on C159 or 153. I don't remember. There is some similar question. So the concept here is that you know, after absorption what would be the concentration of contaminant in biochar, and if you know the concentration of contaminant in biochar and total amount of pollutant you need to remove, you just calculate how much biochar is needed. Okay, there will be homework on that. And precipitations is the process where you can remove metals mostly by making them precipitate with opposite ions. And all for that to occur, a lot of times the ions could be hydroxide ions. If it is hydroxide ion, you are all changing its pH. So all you have to do is control the pH. But a lot of times it also depends on other ion like phosphate. So if you have more phosphate, it will be precipitated out. Again, this is reversible. What is precipitated can dissolve. So this is not a completely permanent removal. Just to know the concept. Okay, so if you increase the pH, it more likely will precipitate because you have more OH ions. Redox reaction, this is something you learn in C153 or in your introduction to chemistry class. So all it means that how much electron is transferred. Okay, so redox reaction is oxidation and reduction both. Oxidation means loss of electrons, reduction means gain of electrons. Your goal is to use this equation to understand how much reactant is needed. Again, I'll connect with the C153 class so that you know. But basically, you have to use some kind of formula like this to calculate your volume of contaminants or the amount of reactant is needed. For instance, here, I'll solve this example so that you know how to use it. For instance, you have organic pollutants can be oxidized by oxygen to produce carbon dioxide and water. So when you use redox equations, you have to balance them one by one. One is oxidation, another is reductions. So I'll do this one again. It's on C153, so I'm just going to go through quickly. Um, Basically, carbon break down to another carbon. Okay, so that's why it goes to carbon dioxide, whereas oxygen will break down to form water. So to balance the equations, there are both two equations. One is oxidation, another is reductions. We'll find that out. So how do you solve it? Again, it's a mass balance. You got to have same number of molecules or atoms in both sides. First, solve the carbon, which is the unique in both one. Um, Hydrogen, oxygen, you can balance by using either protons or water. So that's why first solve everything else. So in this case, carbon. So you have 12 carbon, you have one carbon on right side. So you multiply 12. Now you balance the carbon. Now you have to balance the oxygen. So on the right side, you have, like I said, balance oxygen by using water as a medium because water is present in stormwater. So you have 12 times 2, 24 oxygen on right side, 11 oxygen on the left side. So that means you need another um, 13 oxygen. So that means you can add 13 water. If you add 13 water, it you have 13 oxygen. So now you balance the what oxygen both side. Right side 24 oxygen, left side 24 oxygen. Now next thing you have to balance is hydrogen. The left side you have 22 plus 13 times 2, so that will be 26. So 26 plus 22 is 48. So 48 um, uh, 48 hydrogen is needed. So that means proton because not normally stormwater has proton, so you can use that as a way. So now you balance all the hydrogen, but now you didn't balance the charge because left side has zero charge, right side has positive charge. The only way right side will have positive charge if you remove electrons from the left side or the reactant side. So you have 48 charge, so that means I can say I can take out 48 electrons on the left side. So if you remove electrons, that is oxidation. So that's why we can call this one as oxidations. Now the next one, the way to solve is again, um, you have two number of oxygen, you solve it by adding one more water, so it become two water. And then you have four hydrogen this side, so you can add protons like this. And then to balance the positive negative charge, right side you have zero charge, then left side is positive. The only way you can balance it is by adding four negative charge, and each electron is negative, so you add one electrons. So when you combine them together, you know that you cannot have extra electrons because electrons is not present in water. It has to go somewhere very quickly. So it has 48 electrons. So that means you can multiply this one certain amount to make it 48. So that will be 12. 12 times 4 is 48. So when you multiply, you are adding both sides so that you are not changing the mass. Uh, Equally, you are changing both sides. So now if you add those both equations, you have a total balance equations. It's 22, oxygen 11, plus you have this side, let's say 12 oxygen. I'm taking this one. And let's see, you have a 12 CO2. Now you have to see which side you have more water. On the left side, you have 0 water here. This has 13 water. On the right side, you have 24 water. So that means remaining water 13. If you move the 13 water other side, it will be subtracted. So remaining water will be here. 24 minus 13, it will be 11 water. And if you see the protons, you have 48 protons this side, you have 48 protons. So they cancel out. So there is no protons. So that's the right answers. Okay. So that means basically 12 oxygens, 12 CO2, 11 water. So it says how many moles of oxygen is required to digest 34.2 gram of lactose. So you see that here you need 1 mole of this particular organic pollutants or lactose. Uh, to digest, you need 12 moles. So that's where you know the answers. So 1 mole of C12 S12 O11 is 1 molecular weight, which is basically 342 gram per mole, which is given here. 1 mole of oxygen is if you see oxygen is 16 gram, so that means 2 oxygen would be 32, 16 times 2. So this is O2 is 32 gram per mole. Okay, and so that means you need 12 times 32 moles or 12 times 32 gram of oxygen to to um, react with a 342 gram of um, CSC lactose. So you are asking how much moles of oxygen needed for 34.2. So I'm going to write that here answer because I don't have space. 34.2 gram of lactose. I'm just going to write lactose. Um, you know that 342 gram or 1 moles of lactose is 1 mole of lactose. And you know that 1 mole of lactose requires 12 moles of oxygen. Okay, and 1 mole of oxygen is 32 gram of oxygen. So if you do this one, you'll find the answers. So that will be 10. So that's 1.2 times 32 gram of oxygen. Okay, so whatever that answer is. Okay, so I think this is just redox reactions, and the last one is pathogen inactivations, which is basically you are using certain amount of some chemicals or certain reactants to kill the pathogens. Normally, what you do is you add some kind of let's say bleach, which is hydrogen peroxide, or sometimes people add silver or copper because that's toxic. Usually, that's a dissolved pollutants, and sometimes sunlight. So these are the process people use to degrade. So it's almost close to the end of the class. So what I'll do is I'll not um, go through the biological, that we'll do in the next class. But I just want to end it here that you can use to remove pathogens, you can use sunlight. So that's why you use open channel or pond. For silver or copper, you can add those to a filter media so that it can release that copper or silver ions that will kill them. Or you can produce those process by adding some kind of oxidants like a bleach. But bleach or all those processes are very expensive. You don't want to continue to add to amount. So normally sunlight is more feasible, or UV radiations. A lot of times people use electrochemical process where you add electricity so that it can, because of that charge or the electricity current, the pH will be so different that bacteria will die. Or just by electrons, it create radicals. So these are the design factors. As I said, you can use open water or detention retention pond so that sunlight will kill the pathogens. If you have plants or other things in the wetland, it will not be efficient. That's why you don't want to have plants on the pond for inactivation or removing the pathogens. Um, add silver, copper coated amendments. Again, that's just another way. If you have biochar, you can add all these to work. So that's all for the today's class. And again, I'll go through biological process next class. I just want to show you that there are some quiz questions or learning assessment question you should think of, and you should think of these quiz questions. So next class, in the beginning, I will ask these questions, and we'll have a quiz so that you see whether you can answer this quiz. And some of them require you to read CE153 lecture, so that's also another way to learn it. But again, I'm going to release the quiz today, the quiz one, which is based on quiz one, lecture 1 to 3 at 8 o'clock, around 8 o'clock. You have until midnight tomorrow to answer those quiz. But once you open it, you have 20 more minutes to answer. You not have entire 24 hours. Okay, so prepare well, and then only you start that. Again, if you know the slides, that's all you need to know. You don't need to look for anything else to answer those quiz. Right, so that's all for this class today. It's almost time, and I'll see you next week. Again, if you are one of those which has 5 members, send me email so that I can add another students for your team.
Thank you.
Good luck for the quiz, and see you tomorrow. Attend the discussion session with TA if you need to.